Welcome to your second video in Chapter 3. And this video focuses on the inverse of the exponential functions that we did in Section 1. These are very special types of functions, and we call them logarithmic functions. They are the inverses of the exponential. So if you'll remember from Section 1, we had the exponential where the exponent had the variable, and the b would be the base. We could also write the function as y equals b to the x. And remember, it has an inverse if it passes the horizontal line test, and the exponential functions did. So if it has an inverse, that means you can flip the x and the y. When you do that, you have x equals b to the y. Well, in order to solve this, we do something, we switch it around very easily. And sometimes you can solve it by looking at the exponent. But usually we introduce the logarithm. Now if you'll notice, the log takes on the little base, which is the same base as the exponent. That's very important. The base of the exponent becomes the base of the log. And then you're taking the log of the x value and it equals the y. So first of all, you need to remember this. It needs to be very, very common, and you probably do remember that from Algebra 2. Another little trick is to remember that here you're going to, if you want to go back from the log to the exponential, this is the base. This is what I call the hook. So this is the base. It takes the y as the exponent, and it equals the x. So it comes around here and it equals it. B to the y equals the x. And that will help you get your direction down. Let's try a few of these. Let's complete this table. If we have an exponent, scoot this up a little bit. If we have an exponent form that is 3 to the 4th equals 81. I know that's true. I just want to practice writing it in logarithmic form. So when we do that, we're going to make that 3 be the base of the log. So it'll be log base 3 of 81 equals 4. And some of your exercises are strictly that. Write it in exponential form. Write it in logarithmic form. You're just going back and forth. Let's try this one. So we went that way. If you're given the log base 5 of 1 equals 0, then you can write that in exponential form, because that would be 5 to the 0 equals 1. Okay? If we have 7 to the 1/2 equals the square root of 7, yes, we know that, but if we want to write it as a logarithm, then we have the base of 7, so we have log base 7 of the square root of 7 will equal 1/2. So some of these, this should be review a little bit. We're going back and forth between logarithmic and exponential. You can also use this to solve equations. So I've written, or expressions I guess I should say. I've written 4 of them down here. Now if I say solve the log base 9 of 81, what does that equal? I'm aware you can pick up your calculator and plug it in, but we would like you to get to the point where you can see the relation between the exponent and the logarithm, and it would waste time plugging it in the calculator. So if you let that equal x, then if it's written exponentially and you write it logarithmically, then remember you're going to have 9 to the x equals 81. Well, 9 to the x equals 81. You know right away that x is 2. You didn't have to waste time putting that in the calculator at all. Let's try this one. I'm going to let that equal x. So I'm going to have the base is 3, right? So I'm going to have the base of 3 of x equals the exponent. So log base 3 of x equals that exponent, log base 3 of 1. So we did this base, log of that base of x equals that exponent. Well, look, if they're both log base 3, one is of x, one's 1, do you see how x must be 1? Let's try this one. Again, log base 2 of 1 over 32, let it equal x. And it's written logarithmically, so let's write it exponentially. So we're going to say 2 to the x equals 1 over 32. And that trips people up sometimes. Now, if that was just 32, you could say, oh, well, Ms. Reams, 2 to the 5th is 32. Well, that's great, but I have 1 over 32. So if you know that 2 to the 5th is 32, isn't that equal to 2 to the negative 5th? That would be 1 over 32. Well, here, if my bases are the same, then my exponents must be the same. So x must be negative 5. Now, some of the things we're doing right here in solving these equations are some logarithmic properties, and we get into those in the next unit, the next section. All right, here again, we're going to let that equal x. So we're going to say 16 to the x equals the square root of 2. Now here I was very easily able to make them both base 2. This one was already base 2, and I knew that 32 was 2 to the negative 5th. Well, 2 to the 5th, 1 over 32 is 2 to the negative 5th. Here I've got a 16 and a 2. So I need to rewrite both sides to make them have the same base, and then I can compare them nicely. So 2 to the 4th is equal to 16. So that's 2 to the 4th, and then x equals, right, because this part is 16. And then I can rewrite this as 2 to the 1/2. It's a square root. Well, we did it. We got both have the base 2. So now if this base is the same, my exponents must be the same. Therefore, I can set 4x equal to 1/2, and I can solve for x. I would divide both sides by 4, and x equals 1/8. Okay. When you've got logarithms, there's some shortcuts that mathematicians take. Not because we're lazy, just because we use them a lot and it becomes routine and very common for us to do this. A common logarithm is referred to as a logarithm that has a base of 10. And usually the 10 is understood and not written. We just don't write it. And if we don't write it, it's understood to be a base 10. So if we just write the log of 10 equals 1, that's the same thing as writing the log base 10 of 10 equals 1. Okay, because you know that 10 to the first power equals 10. So if you just see the word log and no base, it's understood to be a base 10, which is nice because the logarithm function on your calculator is already in base 10. Now there is a way to type it in and to calculate a log if it has a different base other than 10. And we will show you that later. Let's talk about natural logarithms. Natural logarithms, much like when we did the exponents, this has a base of e. And this is done so much, we have another shortcut. We usually write this is written as just ln. natural log. I know it would make sense to put the n first, but we put the L first because it's a logarithm. It's a natural logarithm. So we have ln. And there is an ln command on your calculator as well because we use this so much. Now, if you have trouble remembering that, if I just write the ln natural log of 10, that's the same thing as log of base e of 10. So anytime I just write the natural log of a number, that's the same thing as taking the logarithm with a base e of that number. And sometimes that will come in handy, especially when we're solving equations. All right, let's set up and get ready for our graphs. Sometimes we do the graphing and the analyzing first, and then we play with the equations. I reversed it this video. Now I'd like to talk about the graphs of the functions. Now if you'll cut this out on the paper also that we had in class. Again, if you've lost it, you can get another one on Canvas. But I would like to talk about the log functions and the graphs as an inverse of the exponential. So if you'll see on the paper, and I'm kind of stalling for a minute right now because I want you to graph the exponential. This one was the growth. You remember that was the growth equation? So I'm going to label that growth over here. This one was the decay. Right? It's decaying. It was decreasing. And here, another way to think of this is just y equals the log base 3 of x. Remember, that's written logarithmically. We can write it exponentially as 3 to the y equals x. Go back and forth. Let's look at the decay model. If I have this function, and I can rewrite that as y equals log of 1/3 x, and I can rewrite that exponentially as 1/3 to the y equals x. And I'll also go over how to graph this with the different logs. You can do that on the calculator. The different bases, excuse me. All right, so let's review the equations a little bit. This is the growth, so here at 1, 0, 1, and at 1, 3, this was the exponential growth, this is the exponential decay. Remember, they both had intercepts at 0, 1. Well, when you invert that, remember you invert all the x's and the y's. So we're going to invert these. Let's do the growth one first. Instead of at 0, 1, it's at 1, 0. Instead of at 1, 3, it's going to be at 3, 1. And if you'll notice, this had an asymptote. The exponential had an asymptote of y equals 0, the x-axis. The inverse has the asymptote of x equals 0. Okay, now I'm going to highlight that just so that we can make that stand out a little bit differently. Okay, so this is the log graph. Okay, that's this one. Also, when it's decaying, I'm flipping the numbers as well. This still goes through 1, 0. We're going to flip this, and we will pick up here during the part 2 of the video and fill in all the analyzing data for our chart.